Thank you for downloading this podcast from Talk Radio 702 and 567 Cape Talk. For more podcasts and more information on your number one news and talk station, please visit 702.co.za or capetalk.co.za.
Your family, your community, your country, your responsibility. Be the best citizen you can be. Click on the Leaders Say banner on this website to find out about your rights and responsibility.
The Naked Scientist on Talk Radio 702 and 567 Cape Talk with Reedy Clubby.
Chris, good morning.
Hello.
You escaped the worst of the bitter cold in Johannesburg on Monday and Tuesday, I think.
Oh, no, I certainly escaped the cold, but in Grahamstown, I saw rain like I've never seen before. I mean, everyone says it rains all the time in England, but boy, they know how to have rain there.
Wow.
Even by Joburg standards, it was raining hard. I mean, I woke up on Tuesday morning when I was due to fly home. I woke up at about 2 o'clock in the morning to the sound of rain drumming, literally like people drumming on the roof.
Wow.
And on my way driving back to Port Elizabeth Airport, it was raining pretty hard then, but listening on the radio, they were doing the reports of all the different parts of the region, and there were reports coming in of just overnight 47 millimetres of rain in some places coming in. I mean, in East London Airport was closed, so it was really, really very rainy. So actually, I got back here and it was raining, but less. So it felt, relatively speaking, like we were in the desert.
Okay, well, I'm glad that you are safe and sound. I'm sitting here with pictures of you and Ben in action at St. John's. And by the way, a big thank you to our listeners for attending the various shows that you had. And I have a picture of you and Ben. There's a wire and you holding a tube, and there's lots of light and so on. But last week I learned that there was nearly an explosion, and everybody thought that that's what was meant to happen. Can you tell us about that, Chris? What were you doing?
Well, the last experiment, what we did was to demonstrate that when a liquid turns into a gas, it expands by huge amounts. And so what we wanted to do is to show that it expands by a factor of about 1,000. So we got a very strong little plastic bottle and put some liquid nitrogen in it, did the top up, and then put it inside a wheelie bin for safety. And what we were expecting to happen was that the bottle would fill with the nitrogen gas as the liquid turned into gas, taking up a very large volume, and in the end the bottle would fail and go bang. But it took so long for the bottle to actually go bang that we had to put another one in. So actually that went off much more quickly, but then it detonated the other one as well. So we ended up with 2 bangs back to back. So it was quite a loud bang that we produced.
It was loads and loads of fun, I'm sure. Okay, our lines are open for you on 021-446-0567, 011-883-0702. Whatever you want the Naked Scientist to answer for you, he's standing by. Chris in Brixton.
Good morning, Reedy. Good morning, Chris. From Chris to Chris.
Hi, Chris.
Welcome.
Chris, I don't know if you did one of these last week with a train slamming into something, but I've always thought if you were in the unfortunate situation of in a falling lift and you could time yourself exquisitely so that as the thing hit the bottom of the shaft, if there wasn't any rebound, if you leapt into the air at that precise moment, would you save your life?
Oh, hi, Chris. You have to think about it in these terms. When you're descending in a lift, then you have got velocity, in other words, downward speed, at whatever rate the lift is falling. Now, if you jump up in the air, if you want to make it so that when the lift hits the ground, you are effectively not going to be moving anymore, then you would have to be jumping at exactly the same speed that the lift is falling. And this means that you would have to have enough force in your legs to jump to the same height that the lift effectively started from, if you think about it, because that's the only way you will completely offset the velocity that the lift must have. So the answer is, even if you were to jump at the precise moment the lift was hitting the ground, you would still nonetheless only remove from the overall velocity you have going downwards the tiny amount of velocity you would have in the opposite direction. So you'd still be falling very, very fast. It's a bit like if you took it to the logical conclusion, if you were inside a lift that was in free fall from a very high altitude, and the lift was falling at 180 miles an hour towards the ground or something, and then you jumped at the last possible moment, although you would jump and you wouldn't be in contact with the ground at the minute or at the precise second there was an impact, you would only jump up at, say, 10 miles an hour, so your overall velocity downwards would still be, say, 170. miles an hour. So you would still go slamming into the lift floor eventually, albeit slightly after the lift first impacted. So unfortunately, that strategy won't work. And the inventors of lifts have thought of this, and they've actually made them fail-safe because there's a special mechanism on the lift where when the lift is under tension on the cable, then special anchors are retracted from the sides of the lift, allowing it to move up and down in the shaft. But if the cable breaks for some reason, then these anchors are deployed outwards and they jam the lift in the shaft, stopping it from falling. So actually it's really rather difficult for a lift to fall down a lift shaft, and although everyone worries about that happening, it never does.
Okay, Chris, thank you very much for asking that question. Okay, and a tweet from Karabo Siani. Please ask Chris, why is there an echo when you are on a cell phone in a bathroom?
Well, I don't know about his phone, but on my phone there's very often an echo regardless of whether you're in the bathroom or not. Maybe he makes all his calls from the toilet or something. I mean, you can hear when some people are taking calls in rather strange places, can't you, from the sound? But if there's an echo and it's not an electronic echo, because, I mean, there's two reasons an echo can happen. One is because of the physical environment, and the other is because of the way that electronics are working. Sometimes with telephones, for example, and especially with radio studios, what can happen is that when the signal comes in from the outside contributor into the studio should do something called a mix minus. So it sends the person back on the phone a mixture of what's coming out of the radio mixing desk with their own signal deducted from it. And sometimes it doesn't completely remove the person themselves from the mix, and so they hear themselves coming back. But because it's got to go through various digital processing loops, there's a delay, and so you then hear what sounds like an electronic echo. And the same thing happens with telephones. In terms of the physical environment, if you're in a big open space or a room which has got very smooth, flat walls and no soft furnishings to soak up the sound waves, then the sounds can reflect off the walls in exactly the same way that light reflects off a mirror, and you get these sound reflections. And according to how big the environment is, the delay that you get between you making a sound and the sound coming back as an echo will be longer or shorter according to the dimensions of the room. So when you go to a very big space, you get a very pronounced echo because you make a sound, it goes to the far flat wall, bounces back at you, but because the sound has to travel a bit further to get to that wall and then come back to you than it would in a much smaller room, the echo is more pronounced because there's a bigger delay.
Okay, and Karabo, just get out of the bathroom, man. Get out of the bathroom and make your calls. End of the story. Let's go. Gavin in Harry Smith, hi.
Hi, Reedy. Good morning to you. Chris, I have a question regarding ice in my ice tray in my freezer. It produces these stalagmites, is that correct? The vertical ones that go up? How does that happen? They're quite sharp, about an inch long.
Yeah, some people actually have published very nice pictures of these really bizarre, as you say, stalagmites. These, they almost look like towers climbing out of the middle of the ice cube.
Exactly.
And they publish them on the Naked Scientist website. If you go onto a search engine and type ice cubes, Naked Scientist, you will find a reference where people have published these beautiful pictures of doing their own experiment in their own freezers. What we came to the conclusion on this was when the ice starts to form in the ice cube tray, you make the ice, first of all, on the rough bits around the edge of the ice cube tray. And so the first bit of ice to freeze is the surface and the sides of the ice cube, and the last bit to freeze is the water in the center of the ice cube. So as the water starts to freeze, eventually it gets encased in an icy sarcophagus with ice on all sides, apart from a little tiny gap in the center. And because when water freezes, it actually takes up more space because of the way the particles arrange themselves, you end up with actually not enough space in the center of the ice cube to hold the water that's going to turn into ice. So the water gets pushed up, and the only direction it can go in is upwards through the top of the ice cube and in the center. So you get these little piles of ice being pushed up through the center in some cases. And it seems to be more pronounced in some types of freezing than others, and it must be something to do with the rate at which the ice cube is formed. In other words, how quickly the water freezes.
Thank you very much, Gavin. I've got an email here, Chris, from Russell. Russell wants to know, on a recent program on TV, I beg your pardon, hosted by Stephen Fry, it was said that up to 90% of the Earth's oxygen is produced by organisms in the oceans, and that mature trees absorb more oxygen than they produce. I'd like to ask Chris if this is true, and if so, doesn't it make a good case for cutting down the rainforests?
Well, it doesn't make a good case for cutting down the rainforest because although trees may or may not consume oxygen, they definitely draw down carbon dioxide from the atmosphere. So although it's only a temporary source or a storage of CO2, trees nonetheless are sequestering carbon dioxide, and they play a therefore very important role in the carbon cycle, drawing CO2 out of the atmosphere and locking it away as wood, effectively. And when trees rot down, they of course return that CO2 to the atmosphere, but this whole thing's imbalanced. And if you chopped all the trees down at once, then the trees would rot and microorganisms would turn that wood back into CO2 in the air, and therefore you'd dramatically increase the amount of CO2 in the atmosphere with unforeseen consequences. Now, in terms of the oxygen sources on Earth, trees and green plants do make a lot of oxygen, but at the same time, because of the scale of the planet and the fact that 3/4 of the surface of the planet is covered in ocean, the vast majority of the CO2 that gets sequestered and the oxygen that gets produced by photosynthesis actually comes from the sea, and that's from tiny microscopic marine plants called algae. So when you think about where has all the CO2 we pump out gone and where does all the oxygen we breathe come from, it's actually coming from, for the most part, tiny plants which live in the sea.
Thank you very much, Ian. There's somebody who wants to respond to that lift question. Kenny in Claremont, you've got a different take on it.
Hi, Rudy. There is no reaction between your feet and the lift, so you can't jump when the lift is dropping.
Okay, Chris?
I can. Well, it depends. If you were to see, the question was, if you jumped at the precise moment of impact, then you would be able to offset the fall of the lift, your velocity downwards, and therefore you would have net no movement, and therefore you wouldn't slam into the bottom. You'd have to time your jump so that you accelerated away from the lift floor just at the moment it was pushing back on you, if you saw what I mean. So the reason you squish in the lift is because the floor of the lift suddenly stops moving because it's hit the ground, and you, on the other hand, have begun to accelerate up in the opposite direction. So you would actually have to, in some way, jump just as the lift was applying the first force on you in order to offset that, and it's impossible.
Chris, I have an email here, and I want you to believe me when I tell you I've been getting this question for as long as we've been doing the show. And I've just decided, let me just read it because this person is desperate to get an answer. So here we go. Please, 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 there are 3 pleases now. The last time there were 2. Please, 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 ask the naked scientist why it stinks more when a person farts in water, like when you're taking a bath. And why is it that says why is it that quieter farts, the silent one, stinks more than the louder ones? That's it.
We seem to have 1 please for every year we've been doing the programme. So we're into year 3 now. And so we've got 2 questions there. Why do farts in the shower or underwater seem to, as we put it once when someone asked me this, linger longer? And also,
there's a restaurant called Linger Longer here. It's my favourite.
I just like the alliteration, actually. It was almost like a farty sound, wasn't it? The alliteration with the linger longer bit. But also, why do they seem to have a greater degree of malodor if they're silent but violent, as they say? Okay, let's deal with the first one first, the linger longer issue. Mm-hmm. The answer is, when you are wandering around in open space and you drop one, then what's actually happening is that the fart is deployed into your underpants, and it then has to diffuse. In other words, the molecules move out of your underpants, and they are gently diffused into the environment, which means that actually they're spread out through quite a big volume of air. So the overall concentration of fart molecules, which end up in your airspace, is relatively low. But if you go into a confined space, let's take a shower cubicle as an example, the air being exchanged in the shower cubicle is relatively small, and it's already a confined volume. Mm-hmm. Therefore, the initial concentration of the fart in the shower is already higher, so it seems to smell more because the molecules are hitting your nose more often. Therefore, you think there's a high concentration of them, which there is. Therefore, you smell a stronger smell. In terms of when you fart underwater, and it seems to be more powerful, this is because when you fart in the bath, the bubbles are deployed up from between your legs straight into your face. And so you have an extremely high concentration of fart molecules going up your nose initially, and therefore it smells much more to start with. Then a process called adaptation kicks in, thankfully, and you stop noticing it until someone else comes into the bathroom and goes, God, it doesn't smell too good in here. The last question, just remind me what they wanted to know.
Why is it that the silent farts stink more than the loud ones?
Yeah, well, it's probably because of it almost certainly is because of the composition of the fart. What is going on to make farts is that you have a huge thriving community of bacteria living in your intestines, and they are breaking down the food you eat. And they give you actually some of the calories that you get from your food and some of the micronutrients that you need. But they also, in the same way that you burn sugars and turn them into carbon dioxide, which you breathe out of your lungs, when bugs break things down, they also produce gases. Now, some bugs produce very large volumes of gases like carbon dioxide and hydrogen and methane, and these gases are odorless. But some microorganisms produce sulfur-containing gases, including hydrogen sulfide, and these are very malodorous. And so usually what happens when you have certain communities of microorganisms in the gut, when you feed them something that they then digest and make farts from, the bacteria that make the sulfur-containing compounds produce only small volumes of gas, but it's very stinky. Whereas the bugs that make big volume, bulky, what are called bulky farts, they take up a lot of space, and they are big, long farts, but they don't have very high concentrations of the smelly molecules, so they don't tend to smell too much.
Okay, Nico, if you're listening, I have finally asked your question. Now stop it. Let's go to VJ in Greenstone Hills. Hi.
Hi, good morning. I'd just like to know, for carbon footprint measurement purposes, earth-moving equipment consume huge amounts of diesel. We build roads in the rural areas, and I'd just like to know, in order to give back of what we are burning up, how many trees would one plant, for an example, for 500,000 liters of diesel? I tried to go to the website, and the measurement for carbon footprint and what you should pay back is not user-friendly at all.
Mm-hmm.
Yes, I know the feeling. I think partly for that reason, people don't tend to try and put precise numbers on these things, but they tend to look at your total carbon emissions over the course of a year. So we talk about a carbon footprint in terms of CO2 tonnage per year. And we know that the average person, assuming they don't go on any flights and that kind of thing, because airplanes put out enormous amounts of CO2 per mile carried. But if you just take a normal person going about a normal average life, it comes to about 4 or 5 tons of carbon dioxide that is accountable just to you in an average year. And almost half of that is, in a country like England at least, heating your home. So a very, very big carbon footprint is just energy consumption in the home and heating the home and also driving around. And this is calculated on the basis of not just your direct fuel usage, how much diesel you put in your car, but also looking at how much electricity you use, because electricity comes from a high proportion of it fossil fuels, so we can work out what the carbon equivalents in that are, and so on. And so they've come up with these various formulae, which, based on your energy consumption, must translate into carbon, and that's how they calculate it. And a tree, if you think about a very big tree, so in other words, if you're producing 4 tons of carbon every year, a tree might lay down half a ton of, if it's a big tree, you could lay down half a ton of wood in a year. So a tree, when it dies, is going to weigh, 4 or 5 tons, if it's a medium-sized tree. So you might have, in a tree's lifetime, 1 year's worth of carbon emission from you. So you very quickly realise that just planting trees every year is not going to cut it in terms of offsetting your carbon output.
And moving from one carbon-related story to another, is it Jean in Lone Hill?
Yes.
Yes.
Hello, Chris.
Yes, Jean, ask your question.
I would like to know, please, if it's possible to split an atom. Can't you split the CO2 molecule, which is the carbon dioxide, take out the carbon, which you can reuse, and then have the oxygen and use the oxygen again?
Hi, Jill. The answer is that you can do that, which is exactly what plants do. So when a plant is photosynthesizing, in other words, it's got chemical pathways in the chloroplast, the green bits in a plant leaf. What it's doing is picking up CO2, carbon dioxide from the environment. It's using energy from sunlight to then break the carbon dioxide bonds and mix them with water, H2O, to make a new molecule, glucose, C6H12O6, and 6 molecules of oxygen, which then get released into the atmosphere, which we can then breathe. The reason you can't just get hold of some CO2 and use it yourself is because the reason that the chemical reaction that made the CO2 was useful to you is because it produced energy in the process, and CO2 was a very stable product. So in other words, if you want to get the CO2 to be back into the things that you started with, some carbon that you could burn and some oxygen that you could burn it with, you'd have to put the same amount of energy or more in to reverse that chemical reaction. So that's what the plants are doing, and we haven't yet found a better way of doing it than plants have.
Chris, there is a story that's in the Telegraph that I want to ask you about, that surgeons have carried out the world's first transplant of a fully synthetic organ. A windpipe was created using the patient's stem cells and an artificial scaffold. Can you tell us about that?
Yes, this is a gentleman, I think he was originally from Somalia, who was living in Sweden, developed a tracheal tumour, in other words, a tumour in his windpipe. And what they wanted to do was to excise the tumour. But the problem is, if you take the tumour out, how does the person breathe? Because the connection between their mouth and their lungs would have to be removed in order to remove the cancer. Now, you could take tissue from a donor person. The problem is that if you put tissue from somebody else into a recipient, then chemical markers which are on the surface of the cell would not match up, and therefore the immune system would recognise the tissue as foreign, and it would potentially attack it, and this would cause immune rejection. So what scientists have been trying to do over the last recent years is to come up with replacement organs which are actually made from a person's own cells or by a person's own cells, because then there won't be this rejection problem. Now, what they've done with this windpipe, although it may be the first time they've actually implanted one of these things, they've actually been using the technique to produce similar sorts of structures, including blood vessels, from a person's own cells for a number of years now. So what they did was to take out the diseased tissue. They then made a replica model of it using a polymer, a special sort of matrix material, which would act like a scaffolding. They then took stem cells from the person's bone marrow and added them to this scaffold so the stem cells would grow, and the stem cells then turn into the right sorts of cells to make new connective tissue. And they slowly dissolve away the scaffolding, leaving behind just a new replica form of the organ, which can be implanted, and then the person's got an organ using their own cells rather than someone else's, so there shouldn't be any disease risk or rejection risk, and they've got the new organ at the same time. And increasingly, this is what people are seeking to do. And in recent years, there's been a number of very high-profile studies where people have been able to build a new heart, almost, this way, and also a functioning set of lungs this way, and they're also doing it with arteries now as well. I think what's made this one stand out was it was one of the first times that people have put one of these replacement organs into a human rather than just done it in animals.
Does this open up the door, Chris? I mean, if you can create a windpipe, what other organs can we recreate, as it were?
Well, there was a nice paper done recently with hearts and another one with lungs. The way in which they've done this, because hearts and lungs are such complicated tissues, you can't just build a plastic model of those and then expect cells to know what to do. So what they did instead, and so this is proof of principle, they took an organ, say, let's take the lung as an example, from a rat. They then incubated it in a solution of detergent, and what detergent does is it breaks down and kills cells, but it leaves behind all of the connective tissue that the cells hang on. So what you end up with is a scaffolding, which is a replica. It looks the shape of a lung, and it's all of the connective tissue, like the miniature fibres and the proteins that hold it together, but none of the cells are there. Then what you do is add stem cells from the animal that's going to be the recipient, and the stem cells grow all over this scaffolding, and there are messages in the scaffolding that tell the cells what to turn into, and they then become new lung cells, and by doing this over a number of days to weeks, you can make these cells grow a whole new lung for you by growing over this connective tissue scaffolding. And when they did this, they were able to implant this new lung they'd grown into a recipient rat, and the lung actually worked, and the recipient rat was able to breathe using this new lung.
Wow.
Okay, it only worked for a few hours, but at the same time, that was how long the experiment went on for, so they don't actually know how long you could go on for with this. But this is likely to be the future of transplantation, where you take an organ, you use a person's own cells to populate it so it's a genetic match with the recipient person, and you don't have any problem with all of this immune rejection that we have at the moment with organ transplant.
Well, Chris, we'll leave it there. Have a lovely, lovely weekend. Thanks for chatting to us.
Thank you, Reedy. Have a great weekend and see you soon.
Bye-bye. Chris Smith, the Naked Scientist.